So we made these simplifying assumptions of just solar radiation coming in and long wave going out. This is called radiative equilibrium. Why? Because we did not consider any of the atmospheric response, which is what all the weather and climate is basically because of this energy, right? So we also didn't talk about the fact that more energy is received in the low latitudes, less energy at high latitudes. In fact, there's a net gain of energy in low latitudes and a net loss of energy, so we need to move energy and we get winds and ocean circulation, heat transport, everything. But in a local sense also, this simplifying assumption gives us a jump at the surface. So if you just do radiative equilibrium the way we have done so far, then the surface temperature tends to be warmer than the atmosphere just above by assuming these discrete layers. Even though the profile shown here is continuous, this is the troposphere where you have warm surface temperatures decreasing up to the tropopause, where the temperature gradient begins to change because of ozone formation in the stratosphere. This is stratosphere because it is stratified, where there is no energy because it's stable. There is no weather because it's stable. UV, remember the shorter wavelengths from the sun are absorbed by O2 to split into O atoms, which combines with another O2 to form ozone, and then ozone absorbs some more UV and so on. Endothermic reactions give us a warmer temperature. Nonetheless, coming back to this jump, in the real world we have what is called convection. When you heat the surface, air is going to warm and rise, and there is evaporation as well and so on. So that jump or the discontinuity at the surface is going to be removed by convection. So you can do what is called radiative convective equilibrium to remove these jumps. But we'll jump to something else in the meantime. It's called climate feedbacks. Why? Because we have enough background now to think about what is the impact of increasing greenhouse gases. We want to know whether increased greenhouse gases trap more energy and how that energy change in the balance, delta, is going to affect the surface temperature, right? So dTs dq is what we are looking for, sensitivity of surface temperature to the perturbations in the net energy balance. That's what we want to find out, and we call it climate sensitivity. Okay, so emitted radiation per unit area is sigma Te to the fourth. Going back to our simplifications, we just assume there is some layer where the effective temperature is going to determine how much energy is being lost, and then we take a partial differential of this. You have to learn that by yourself. I'm not going to teach that part. So delta Q is this one, the energy flux. So delta of sigma Te to the fourth is going to give us 4 Te to the cube, 4 Te to the cube, I'm sure you know how it works, times delta Ts. We have replaced Te by Ts here, assuming that any sensitivity of the emission temperature is going to be directly related to the changes in the surface temperature as well. Another simplifying assumption, but it doesn't matter because we can plug in the numbers and get a sensitivity of temperature change with respect to perturbation in just the blackbody radiation balance is only 0.26 Kelvin per watt per meter squared. That is little too small. Okay, you can convert the increase in greenhouse gases to increased greenhouse effect, which gives you delta Q, and then this is the delta Ts that this equation predicts. But we know it's too small because we know the change in radiation balance so far and the increase in temperature. What do we have to add? Obviously, there are climate feedbacks in the system. If you increase temperature by increasing greenhouse gases, you are immediately going to increase water vapor because warmer air holds more moisture. So we go back to our Clausius-Clapeyron, the partial pressure of water vapor related to some constant times exponential beta T, right? Water vapor is going to depend exponentially on air temperature, so it's our biggest nonlinearity in our system, makes for a lot of difficulties. You do the differential of that because it's an exponential, you get DES or EE, equilibrium, beta dt. So we look for response of the surface temperature now combining the black body radiation and water vapor feedback. It's going to almost double the sensitivity to 0.5 Kelvin per watts per meter squared. Is this complete? Of course not, because you then have to add clouds, you have to add melting of glaciers, albedo changes, vegetation changes, all sorts of things, right? Calculating climate sensitivity is a very difficult task. A great estimate, the most up-to-date estimate, has just been published a couple of months ago in 2020, but that should tell you that this is complicated business and you still have a lot to learn, but so do the scientists, because we still keep estimating these. Okay, so you can do this kind of problem from the homework by taking n slabs in the atmosphere, do the solar radiation coming in, outgoing long wave, transmittivity, exchange between the layers, and so on. You can use the same equations and add up, and you get a simplified expression, so it's not too difficult. I'm not going to do it, but I'm going to end the chapter by showing you Max Planck, who combined the Wien's, remember the law we saw, lambda m times t is constant, Wien's displacement law. Maximum wavelength of emission is related to temperature through a constant, and the Rayleigh dispersion relation. So he combined those to produce this very complicated expression that I'm not going to go into, but the book has it in an appendix. You should look at it just to get awed by the complications. In climate models, which we haven't talked about yet, the radiation transfer calculations are the most complicated, most detailed, and most expensive in terms of how long it takes for the model to integrate. That's critical, because if you want to make a forecast for next day, your model must integrate within that 24-hour period so you can say what's coming next, right? Model cannot integrate longer than 24 hours to make a 24-hour forecast. So radiative transfer calculations are constantly being improved to reduce the time it takes, and so on and so forth. That concludes this chapter on energy balance, but go through it again, make sure you understand it. It's fairly straightforward in terms of the concepts. Actual calculations are complicated, but the basic concepts are fairly straightforward, which you should master.